Okay, let's consider the following. Think of an investment of 100 rupees
Okay.
that earns a simple interest of 50%
Okay.
per year. So, at the end of 1 year, this 100 rupees becomes 150 rupees.
Yeah.
Yes.
At the end of the second year, it grows to 200 rupees.
Yes.
Third year, it is 250 rupees. So,
Yes.
at the end of n years, it is going to be 100 plus 50 into n.
Yeah.
Is that right?
Yeah.
So, can you plot the graph of the amount versus years?
Yeah. This is my money
Mm.
and this is time.
Okay.
But I am only plotting the years.
Mm.
So say this is 1 year, 2 year, 3 year, 4 year, 5 year, something like that. So at the 0th year, I had invested 100 rupees. So say this is my 100.
So, that is your principal amount.
That is principal.
Mm.
At the end of 1 year, it will be 150, 200, 250, 300, like that. So I will get a graph like this. So it will be a straight line graph.
So, the equation of the trajectory of the money growth is a straight line.
Yeah.
Yes.
So the
What is
graph.
its equation?
So the graph will look like y is equal to 50x plus 100.
Yes. So, the equation of the trajectory is y equal to 50x plus 100.
Yeah.
Yes.
Yeah.
So this is same as the graph of the distance versus time of a particle traveling with constant speed of some 50 kilometers per hour.
Yes, you are right. So, let us now look at the same amount of money,
Okay, that
right?
means 100 rupees.
Which, yeah, same amount of money, which is 100 rupees. And we compute the growth,
Okay.
but compounded every year,
Okay. And the rate is 50% only.
50%.
Okay. So then, like after 1 year, the amount will be 100 into 1 plus 50 by 100.
Yes.
That will be, it is 1 by 2, so it will be 150.
Correct.
Similarly, at the end of 2 year, it should be 100 into 1 plus 50 by 100 power 2. Just calculate it, what it is.
So
It is 225.
yeah.
Similarly, after 3 years, it should be 100 into 1 plus 50 by 100 power 3.
So, it comes
That
out to
is
be
337 rupees 50 paise.
okay.
So,
So in general, for a nth year, I can say that after n year, the amount should be 100 into 50 by 100 power n. Or I can write it as 100 into 1.5 power n.
okay.
Yes.
What is its trajectory?
So the trajectory will be a polygonal line.
Having corners?
Yeah, having corners at 1, 2, 3, etc.
Yeah, it
Okay.
should be something, because in between I will have something like this. So in between it will be straight line, another straight line, another straight line. So it will be a polygonal line.
So, you see that it abruptly changes
Yeah.
at the end of every year.
Yes.
Is that right? Let us now look at the same amount of money, right, compounded at 50% per annum, but compounded every 6 months
Okay.
in a year.
So here also our principal amount is 100 rupees. Now since we are calculating every 6 months, so there will be a factor of, since 50% is the annual rate, so there will be a factor 2 here, and so at the end of 6 months the amount will be somewhat about 125.
Yeah.
Okay. Then
Similarly, at the end of 1 year it should be
156 rupees 25 paise.
1.
56 rupees 25 paise. 156.
Yeah. So you see that the amount grows.
In general, the formula will be
Mm.
after n years. If I want to calculate, it is after 6 months I am doing. After 1 year it is 2. So after n year the amount will be, or I can write is at 100 into 1.25 power 2n
Yes.
Fine.
at the end of n years.
Yeah.
Yes.
So it is at the So you see that the amount keeps on increasing.
Yeah.
So my question now is, what if I compound the interest every 3 months?
Oh, then also we have to use the same thing.
Ah,
Yeah.
So we will get instead of this 50 by 200, it will now be 50 by 400.
400.
yes.
Yeah. And power 4n.
Yeah, it will be power 4n.
Yeah.
Yes.
So at the end of n years, our formula will be 100 into, what is this, 1 by 8,
1.125.
125.
Okay, fine.
So, ma'am, I observed that the same amount with the same rate of interest yields more and more when we compound it n times, and as n keeps increasing, we get more and more amount.
Okay. Now take the principal amount to be 1 rupee
Okay.
and the compound interest is 100%.
Oh.
No, I give 100% return.
Yeah, you compute.
If they are giving us 100% returns.
Yeah.
Anyway.
Ah,
So after 5 years, I have to calculate. So the amount will be 1 plus 100 by 100 power 5, and this will be 2 power 5, which is 32 rupees.
okay.
Yes.
So at the end of 5 years, 1 rupee which fetch with compound interest of 100% yields 32 rupees.
Yeah.
Yes.
So now take the same amount, namely 1 rupee,
Okay.
and if it is compounded every 6 months,
Okay.
Okay.
what
So-
happens to the amount at the end of 5 years?
Then the amount will be, I will again have a
100
factor
by
of
200.
2. Yeah,
Hmm.
that is 10.
Yeah.
Can you calculate it?
So that will be 57 rupees 66 paise.
Okay, fine.
Shall I tell you if I compound every 3 months, what will be the answer after 5 years?
Yeah, I see that you are following the discussions very carefully
Yeah.
with full concentration. Go ahead and calculate.
So that case it will be 100 by 400 and it will be 4 into 5, that will be 20.
Okay. What is the amount?
It is 86 rupees 74 paise.
Yeah, 74.
Yeah.
Okay, so you see that the amount grows. So you expect that if it is compounded every instant, then the amount will go bigger and bigger.
Yes.
I guess it will go to infinity.
Do you think it goes to infinity?
I
Let us
guess
see.
so.
Let us work out the details. So what we would like to see is the principal amount is 1 rupee. We are going to compound it with interest 100%.
Okay.
And we do it n times in a year.
Okay.
So let us form the table of values.
Okay.
So at the end of 1 year, we would like to see
So our principal amount
this
is
1 rupee,
rupees
and I am going to
That is my
compound it, say n times in a year.
n times a year,
Yes.
I'll be ready with the calculator so that I can
and
give the
the
value.
rate
Yes,
is
sir.
100%.
The rate is 100%. So let's form a table of values. Put n. Let the first column be n. And the second
at
column.
the end of 1 year only I have to calculate.
Yeah, exactly. So at the end of 1 year, what is the amount? So you just write amount at the end of 1 year.
So we are compounding n times.
N times in a year.
So n is the number of times we compound in a year.
Exactly. Right. So let us take n to be 1, and then what is
we
the
have
value?
2.
Yeah, the answer is going to be 2.
Yeah.
Yeah.
Then suppose you do it 2 times a year,
Then 2.25.
right? 3 times a year,
2.37.
okay. What about 4 times a year?
2.44.
It is not increasing that much.
5,
2.48.
okay. Then 6,
2.52.
then 7,
2.54.
then 10,
2.59.
okay. 50,
Oh, sorry, it is at 10.
10,
At 10, what is the value?
2.59.
okay. 50 times I would like to
My God,
do.
that's a big number. 2.69.
Oh,
What about 60?
2.696.
2.696.
Yes.
Yeah, I would like to increase n.
Okay.
What happens if I do it 100 times?
Oh,
I am just writing
Yeah.
name and amount.
Yes, fine. So what happens if you do it 100 times a year?
2.705.
Okay. What about 1000 times a year?
2.7169.
10,000 times a year?
2.71814.
Okay. What happens when I do 10 lakh times?
It is 2.71828.
Okay. What if I do it 100 lakh times?
1 crore. 2.718281.
So do you see what is happening really there?
Yeah, the total amount at the end of the year keeps increasing as n increases, but it is definitely bounded.
Yes. So can you tell me what is the total amount?
So total amount is exactly 1 plus 100 by
Mm.
n into 100
Mm.
power n.
Correct.
Which
What is
nothing
it?
but 1 plus 1 by n power n.
At the end of 1 year.
1 year.
All right. So when a principal amount of 1 rupee is compounded n times in a year, that's what you have given.
Yeah.
So 1 plus 1 by n to the power of n. As she said, it grows, it increases, but certainly we see that it's bounded.
Yes.
But mathematically we have to show this.
Yeah.
So suppose I call by an 1 plus 1 by n to the power of n, right?
So this will be a
Then
sequence.
it is a sequence.
Yes.
And I have to show that this sequence is an increasing sequence and it is bounded above, isn't it? That is what we have to show. So will you try to show that this sequence an is an increasing sequence and it is bounded above?
Yes,
Yes,
ma'am.
ma'am.
So try to give me a proof. I will be back in a minute.
Okay.
Yes.
Ma'am, can we use the board to try the problem?
Yes, sure, you can.
Okay.
Yeah. Let's go to the board. Maybe you each one of you take half of the board and then try to work out the details. I will be back.
Okay.
Yes. able to show?
Yes,
the
ma'am.
AN is an increasing sequence.
Yes, I just finished.
Good. Let's see. What does he do? Yes, yeah. Okay.
Yeah.
Fine. Okay, let's listen to her proof first.
Yeah.
Yeah, there are different proofs already. So I'm trying to show that an is an increasing sequence by showing that the ratio an plus 1 by an is greater than or equal to 1 for all natural numbers n. So I'm computing an plus 1 by an. So the ratio an plus 1 by an is 1 plus 1 by n plus 1 power n plus 1 by 1 plus 1 by n power n.
Yes.
Then I'm doing simplification and all that. Then from here I'm getting that this is equal to 1, this term inside this bracket is equal to 1 minus 1 by n plus 1 the whole square power n plus 1. So this is greater than or equal to 1 plus 1 by n into 1 minus n plus 1 by n plus 1 the whole square.
Fine.
And then I am simplifying and I am getting that this is equal to 1. So I have shown that an plus 1 by an is greater than or equal to 1 for all n. So
But in that inequality, I
Yeah.
think you have used something like 1 minus x power n is greater or equal 1 minus nx, right?
Yeah. Can you
But
show that?
how we will prove?
yeah. So this we can prove by induction, right?
Okay. Try.
So the basis step is n is equal to 1. That is trivial. And then let me assume that this is true. So for n is equal to 1, it is true. For n less than or equal to k, I am assuming that it is true. Assume that this is true.
So that is your induction hypothesis.
Yeah.
Yes.
So I need to prove for n is equal to k plus 1.
Fine.
So 1 minus x power k plus 1 is nothing but 1 minus x into 1 minus x power k.
Fine.
By induction hypothesis, I already know that this is greater than or equal to 1 minus x into 1 minus kx.
But I need 1 minus x to be positive, is it?
Yes. Yeah.
Hmm.
So we need know that x is so we need x to be greater than or equal to minus 1. Only then all this will hold. So
And less equal 1. 1 minus x should be positive.
1 minus x must be positive.
Yeah.
What
So
are you-
this must be less equal 1.
Yes.
It is all right.
Okay.
So this is equal to 1 minus k plus 1 into x plus kx squared.
Fine.
This is nothing but this is greater than or equal to 1 minus k plus 1 into x. So we have proved it by induction. We have proved this by induction.
Fine.
Yeah.
That you have used in this step.
Yeah.
Mhm.
From here
From
to
here
here.
to in this step. Fine. Right. So it's an easy proof.
Yeah.
Which shows that an is an increasing sequence.
Yes.
Okay, let's go to his proof.
No, I have just used AMGM inequality.
AMGM inequality.
Yeah.
Okay, fine.
So I need to prove this.
That's
have
your AN.
It's my aim to prove. So it can be written as this form also.
Yes.
Yes, fine. Correct.
Now I am taking a n plus 1 terms, y1 as 1 and y2 to yn plus 1 as 1 plus 1 by n.
Fine.
Then the gm will be 1 into this many terms, that is power n, power 1 by n plus 1.
Yes.
So it is power n by n plus 1.
Correct.
Less equal, the am will be 1 plus n such terms are there,
Yes.
and this can be computed as 1 by 1 plus 1 by n plus 1.
I just want to make a remark. The equality sign will not be here because these terms that you have considered are they are all distinct.
Yeah, yeah, 1 and these are distinct.
Yeah, they are distinct. So,
So
it will be a strict inequality.
Yeah, it
Yeah.
will be.
Yes. Fine. Continue. Then.
Yeah. Then this will fetch me that 1 plus 1 by n power n by n plus 1 will be less than 1 plus 1 by n plus 1. Now I take the n plus 1 at power.
This is your
that will
AN.
give.
That's your AN plus 1.
Yeah.
Yes.
So it again shows that AN is an increasing sequence.
In fact, a strictly increasing
Sequence.
Yeah.
Yes.
Exactly. So both your proofs are fine, but I have another proof.
Oh,
So let's see what it is.
I think that must be more ingenious.
No, let us see. So I take 0 less than A less than B
Okay.
And then consider b power n plus 1 minus a power n plus 1.
Okay.
Okay.
This is equal to
B minus A into b power n
b power n
plus a b power n minus
a
1.
b power n minus 1
Yeah.
plus a square b power n minus 2 plus etc. plus a power n minus 1 into b plus a to the power of n.
Yes.
So this will be less than b minus a into, there are n plus 1 terms.
Yes.
So it will be n plus 1 into b to the power of n.
Yes.
Alright.
Yes.
Hmm.
So that gives me b power n plus 1 minus a power n plus 1 by b minus a to be less than n plus 1 into b to the power of n.
Yes.
Hmm.
At this stage, I take my b to be 1 plus 1 by n
Okay.
and a to be 1 plus 1 by n
Okay.
plus 1.
Okay.
So substitute for a and b. Is that okay?
Okay.
So that gives me 1 plus 1 by n raised to the power of n plus 1 minus 1 plus 1 by n plus 1 raised to the power of n plus 1 divided by b is 1 plus 1 by n and a is 1 plus 1 by n plus 1.
Okay.
Hmm.
So that's the left hand side. And that must be less than n plus 1 times b power n. So it's 1 plus 1 by n raised to the power of n.
Hmm.
Yes.
So let's simplify the left hand side. So this gives me n into n plus 1. So I'll have n plus 1 minus n plus 1. Alright.
N plus 1 minus n.
And that will give me
1.
n into n plus 1 because this denominator is n into n plus 1 multiplied by, here I write this as 1 plus 1 by n raised to the power of n plus 1, and that I write as 1 plus 1 by n into 1 plus 1 by n raised to the power of n.
Okay.
And you know our sequence an is 1 plus 1 by n raised to the power of n.
Yes.
So the first term is this multiplied by an,
Yes.
and the second term is
Is
simply
an plus
a n plus 1.
Yes.
Right? That must be less than n plus 1 into 1 plus 1 by n raised to the power of n.
Yes.
Clear? So this will give me, I can cancel this
Yes.
and then simplify n plus 1 multiplied by an minus n an plus 1 is less than
An.
1 plus 1 by n raised to the power of n,
That
which
is
is
an.
an.
Yeah.
So n plus 1 into an minus an, that will give me n an is less than n an plus 1.
Yes.
This is true for every n which is a natural number.
We can cancel out n.
This implies that an is less than an plus 1
Hmm.
for every n in the natural number set.
Yes.
Which proves again that an is an increasing sequence. But
Yes.
what is an? An is 1 plus 1 by n raised to the power of n. And what is it? We should come back to our problem.
Yeah.
So, what is it? Tell me.
It was the means after 1 years the principal price or the amount when we are compounding at a 100% interest rate yearly, we are compounding n time.
It takes the value which is close to some
2.71.
71828. And we have shown that it is an increasing sequence, but one thing that remains is that
We have to show
it is a
bounded sequence. Yeah.
Start with the an is 1 plus 1 by n raised to the power of n.
Yeah.
Okay? So this will be sigma k equal to 0 to n nck into 1 by n power k.
Yeah.
Binomial theorem.
So this gives me sigma k equal to 0 to n into n minus 1, n minus 2, etc. up to n minus k plus 1 divided by k factorial into 1 by n power k.
Yes.
I rewrite this as sigma k equal to 0 to n minus 1, n minus 2 up to n minus k plus 1 divided by n power k into 1 by k factorial. But so this will be less than sigma k equal to 0 to n 1 by k factorial.
Yes.
Right? Because
Every
there are
Because
k such
each term,
factors and I have
Yeah.
by n to the power of k.
Hmm.
And that will be, right, equal, that will be less than, again, 1 plus 1 plus 1 by 2 plus 1 by 2 square plus etc. plus 1 by 2 to the power of n minus 1.
Yes.
Yeah.
Is that right?
Yes.
So that will be less than 1 plus sigma k is equal to 0 to infinity,
Yes.
right? 1 divided by 2 to the
power.
power of k.
Okay. Yes.
And that is 1 plus, what is this? The sum 0 to infinity, it's a geometric series.
Yes,
Yeah.
First
yes.
term 1
Half.
and common
It will be
ratio
2.
half. So that will be 2 and
Yes.
so that's equal to 3. So this tells us that the sequence AN is bounded by
3. Oh.
We already have shown,
Shown that it is an increasing sequence.
it is an increasing sequence and it is bounded by 3. That is what we wanted to show.
Yeah.
Is that
Yeah.
right?
Yes, ma'am.
Okay. So then,
So this means that the amount of 1 rupee compounded with 100% interest per annum at every instant is not a big doesn't yield a big amount as expected. It is nothing but the limit of this sequence AN, that is this sequence AN is equal to 1 plus 1 by n power n, and we know that the limit of this sequence is E, and that value is close to 2.71828.
yeah, it's close to 2.71828. So the table of values
Yeah.
that we have computed tells us that it is close to this value.
Yes.
Yes, that's fine. So it is the amount of money that is accrued when a principal amount of 1 rupee is invested with 100% per annum interest compounded continuously. Isn't it?
Yes.
Yeah.
So that is what is E, and this E plays an important role in mathematics and its applications. And the function e to the power of x is called the exponential function, and you can show that e power x is limit as n tending to infinity of 1 plus x by n raised to the power of n.
Yes. Okay.
And here comes my question. So do you know of a function whose derivative is itself? Or in other words, my question is, do you know of a function f of x such that d by dx of f of x is f of x?
Yeah. I already told e power x is one such function. So let me try to prove that the derivative of e power x is e power x.
Fine, show me.
So I'll prove d by dx of e power x is equal to e power x. Let's take f of x is equal to e power x.
Fine.
We know d by dx of f of x is nothing but limit as h tends to 0 f of x plus h
Fine.
minus f of x by h.
Right.
So d by dx of e power x is limit as h tends to 0 e power x plus h minus e power x by h. This is nothing but e power x can be taken outside into limit as h tends to 0 e power h minus 1 by h.
Right.
We know the expansion, series expansion of e power h. This is nothing but 1 plus h by 1 factorial plus h squared by 2 factorial plus etc. So e power h minus 1 will be this term, divided by h we will have 1 by 1 factorial. So we will have e power x into limit as h tends to 0 of 1 by 1 factorial plus h by 2 factorial plus h squared by 3 factorial
Fine.
plus etc. The limit of this as h tends to 0 is nothing but 1. So, it is e power x.
Okay, so you have a function whose derivative is itself.
Yes.
Fine. Why do you say that you have one such function?
Because like if I take any constant multiple also, then also it will work. So any constant multiple of c.
So, c times e power x also has the property that d by dx of c e power x is c to the power of x.
Yes.
And so, you say that e power x is one such function which possesses this property.
Yes.
Fine, that is good. Okay. So, we will continue our discussions later on.
Okay.